Okay, good morning again. And buenos dias to our friends in Latin America that are joining us. This webinar is serving folks in North America and Latin America regions, and there may be others worldwide that have joined as well. This is Hal Green, and I manage marketing for Geophysical Insights, and we're delighted to welcome you to our continuing webinar series that highlight applications of machine learning to interpretation. We also welcome Dr. Tao Zhao, our featured speaker, who will present on leveraging deep learning and extracting features of interest from seismic data. Dr. Zhao and I are in the offices of Geophysical Insights in Houston, Texas, along with Laura Cuttle, who is helping at the controls. Now, just for a few comments about our featured speaker today. Dr. Tao Zhao joined Geophysical Insights in 2017 as a research geophysicist, where he develops and applies shallow and deep learning techniques on seismic and well-logged data and advances multi-attribute seismic interpretation workflows. He received a Bachelor's of Science in Exploration Geophysics from China University of Petroleum in 2011, a Master's of Science in Geophysics from the University of Tulsa in 2013, and a PhD in Geophysics from the University of Oklahoma in 2017. During his PhD work at the University of Oklahoma, Dr. Zhao worked in the Attribute-Assisted Seismic Processing and Interpretation, or ASPI, consortium, developing pattern recognition and seismic attribute algorithms. And he continues to participate actively in the ASPI consortium, but now as a representative of Geophysical Insights, and we're delighted to have Tao join us today. And at this point, we're going to turn over the presentation to Tao and get started.
So hello to everyone, and thank you, Hal, for the introduction. And as you can see the title, today we will talk about how we use deep learning in the application of seismic data interpretation. And we are focusing on extracting different features of interest from seismic data. And here is a quick outline of today's presentation. And first of all, I will pose you a question on how we see a feature on the seismic data versus how a machine or how a computer sees a feature on the seismic data to link to the reason why we want to use deep learning. And then there's a very interesting story or argument behind the shallow learning versus deep learning method, because today we're only focusing on deep learning. So shallow learning is another main topic that people work on to be applied in seismic interpretation. And then there are three main applications I will talk about today. The first one is seismic facies classification. The second is fault detection. And the last one is channel extraction. And finally, there will be some conclusions to go with the this presentation. So the first thing I want to talk about is actually a question. So what a human interpreter sees versus what a computer sees on a seismic image. So here we have an example from offshore New Zealand Taranaki Basin, and on the left you have a vertical seismic line and of seismic amplitude, and on the right you have a time slice from a coherence attribute, just to show you how complex the geology is in this region. And as human interpreters, we have no problem to see features of different scales from this seismic image. For example, we have some geophysical phenomenon here. First of all, those are multiples, and those are features that we see from the seismic data that may not relate to a specific geological feature. But here we have something that has a specific geologic meaning. So here we have some stacked channels, and here we have a volcano, and here we have tilted fault blocks, and here we have very well-defined continuous layer sediments, I would say. So as human beings, we have no problem to identify those features because we have very good cameras and very good processors. Our cameras are, of course, our eyes, which helps us to identify those features in a both very local scale or very tiny scale, as well as to capture the features in a very large scale, such as the whole package of the stack channel. And on the other hand, we have a good processor, which is our brain. And our brain can understand or can put the information together from both the local patterns and the very large scale patterns. But for a computer, there's a problem because by default, a computer only sees pixels from this image, which means the computer only understands the intensity at each pixel. So for a computer to understand this image, typically we need to provide a suite of attributes for the computer to work on. And for example, in the stack channel, and we have several attributes that can quantify the stack channel facies. But those attributes are not perfectly aligning in the same region. And in this particular region, we have reflectors that are converging into each other. So a attribute that quantifies the convergence of the reflectors may best quantify this kind of feature in this local scale. And here we have discontinuity within those reflectors. So some coherence type of attribute may best quantify this feature. And here we have continuous layer but gently dipping. So maybe just as simple as the dip of the reflectors may quantify this local scale features. And finally, we have some very weak amplitude here. And so we can just use the mean or the mean value, not the mean value, but the envelope of the amplitude to quantify here. So in short, that each of the attribute may quantify a particular region within a big geologic facies, but not everywhere. So then the problem we have is how can we quantify this complex patterns in this relatively big window as one uniform facies? So and the end goal is we wanted to have something like that. We want to color code the same seismic facies into the same color, into one uniform color represented by one uniform value. And for example, here we have all those facies color coded, and all those transparent regions means that we don't have a facies assigned. Well, actually, we have a facies assigned. We can call it a facies 0 that represents everything else. So in the later, although this result is from interpreter's manual pick, but I will show you in the first application that after we train a computer, after we train a deep learning model, that a computer can do a pretty good job to mimic those pickings on other seismic slices. But before I go into the actual applications, let me share with you a very interesting story. So here's a bet between shallow learning and deep learning, and the bet was happened in 1995, and on March 14th is almost 24 years ago. So the bet was between two very famous figures. On the left is Vladimir Vapnik, who is the inventor of support vector machines, and on the right is his boss at Bell's lab at that time. So one day that Larry Jekyll, this guy, bet that after a few years that people will have a good understanding on the big neural network or the deep neural networks, and people will start using those deep neural networks with great success. And then as a counter bet, Vapnik thinks that even after 10 years that people will still having trouble with those big neural networks, and people may not use those anymore, and they will turn to kernel methods such as support vector machines, which are shallow learning methods. And they bet on a very fancy dinner. So after 5 years, it came out that both of them were wrong, because by the year 2000, people were still having trouble to use the big neural networks, But however, people are not dumping, were not dumping the neural network at all. I mean, they were still using that, and so Vapnik lost as well because people are still using neural networks. And in fact, after 10 years from that time to the early 2010s, and people were actually starting to use very large, very deep neural networks, such as convolutional neural networks. So as a result, both of them lost the bet, and they had to split the dinner. And guess who had a free dinner? It's Yang LeCun, who happens to be their witness at their bet. So as we all know, that Yang LeCun is one of the founders or inventors of the convolutional neural network that we use today. So then there's a question about what is shallow learning and what is deep learning. Well, different people may have different answers, but for me, I think the main distinction between shallow learning and deep learning is if a algorithm learning from the features provided by the user, or the algorithm learning the features by itself. So if we're using a shallow learning method, such as a typical neural network, a multi-layer perception neural network, and the first step to do if we apply the neural network on the seismic data is to extract seismic attributes and let the neural network classify on those attributes. So that means the algorithm needs to learn from the features, and here features means seismic attributes. But on the other hand, if we're using a deep learning method to classify on seismic data, typically we will provide the raw input, which is the seismic amplitude. You know, some people may use even pre-stack seismic amplitude, and here we're just using post-stack, but it's still a relatively raw data compared to the seismic attributes that we calculated from the seismic amplitude. So during the training process of a deep learning method, it will automatically derive a bunch of, or a great number of I would call it attributes from your raw input data, and find the best ones that represent the data so that your target classes can be well separated. So for example, here we have two seismic facies. One is a stack channels, and the other is a tilted fault block. And if we want to separate those two features using a shallow learning method, and this is what we're gonna do. We have to choose a bunch of seismic attributes that best distinguishing those two facies. Maybe we can use discontinuity, or deep magnitude, or amplitude variance, or even reflector convergence. But the problem is, even if we use all those attributes, probably we won't have a perfect separation between those two facies, because those patterns are so complex, and at every region they have a different response from a particular attribute. But don't get me wrong, that I'm not saying that those attributes are useless, and we don't need to use seismic attributes at all. I mean, seismic attributes are very useful to quantify local properties, and they're very useful for visualization purpose, because once we have a seismic attributes, it's very easy for us as human beings to identify the features. It just becomes difficult for a computer to use those information and separate those very complex patterns from the others. So what are we gonna do? So how to quantitatively describe the difference between those two very complex facies? Well, the answer is let the machine tell us. So if we are using a deep learning method, and here, for example, I'm showing a very simple deep learning model, and people call it encoder-decoder model. And then we just feed in this seismic amplitude data, and after training, we will have a classified seismic facies, just like I showed at the very beginning, that color code different facies to a single color, and according to what training data that we provide. So for example, here it classifies the stack channel into one uniform color, or one uniform or a single value, and here the tilted fault blocks in another value. So deep learning automatically learns the most suitable attributes to use, although those attributes may most likely won't make any sense for a human being if we just look at those attributes, but the computer or the algorithm can figure out the difference, or to use those attributes and to separate your target fishes. So let's look at the first application. The first application is on seismic facies classification on this data set that I used in the introduction. And this being a testing data set is relatively small, about 1 gig in size. And and because I did this study almost a year ago, so at that time it took me about 90 minutes to run the training on a not that powerful single GPU. Right now, with the growing computing powers and with a better scripting and better software libraries, and we can do it much faster. So there's 31 lines are manually annotated from this seismic volume, and those are used for training and validation. For example, and we can uniformly interpret or annotate some of the lines in this volume, and those are the annotated lines. And we can train a model using, let's say, 29 lines and testing your result on 2 lines that are not used in training. And we can also do a cross validation, which means we can choose, so the first time we choose this 29 lines and test it on the other 2 lines, and the next time we train on a different set of training data, a different 29 lines, and testing on the other 2 remaining lines. And after several rounds, if we have a relatively stable result, then we know that our model parameters are pretty good to use, and the result is pretty reliable. So here is the result on the training data after we run the training. So this is a line that's used in training, and this is the manually interpreted result. And as you can see that there are several seismic facies, and whether it's geologically meaningful or it represents a particular geophysical phenomena, those facies are being picked out by hand. And after we run the training, first of all, we want to test the neural network on those training data to see if the network is converged well and behaves well on the training data. So this is the result on the same training line. As you can see that if I flip back and forth, and as you can see, those 2 images match very, very good, and which is good, but it's not that interesting because this line is used in training. And what we really want to see is how the neural network performs on a testing line that is not used for training. So this is a line that's not used in training, and this is a hand-picked result. We consider it as a ground truth, and this is the predicted result on the same line. So this gives you an idea of how this network performs on data that it hasn't seen before. And to measure the performance or measure the quality of the prediction, we have several options in terms of the performance metric. And the most commonly used one is maybe the sample accuracy, which means how many samples are correctly predicted. And here is 93% of samples are correctly predicted. But in this case, this metric is okay to use because we don't have a huge imbalance among all those classes. But in some cases, particularly if we're looking for features that only consist a fraction of samples in your data set, such as if you want to pick out only faults, then this metric is very misleading, because let's say if you only have 0.1% of your data are faults in your data set, then even if you don't predict anything for the fault and get all the remaining and predict every sample as non-fault, you still have a 99.9% correctness or accuracy, but in fact you have nothing predicted for the fault. So a more robust, I would say, more robust metric to use is this intersection over union, which is defined like this. So for a particular class, let's say for the stacked channel complex, we take the ground truth of the stacked channel complex, which is outlined by this region, and the intersection between the ground truth and this predicted result. So divided by the overall extension of your ground truth and this predicted result. So basically, it calculates how much overlap you have between your prediction and your ground truth, and this is only for one class. If you have more than one class, for this in this example, have 9 different fishes, we will average over this measurement over all your classes, so that it essentially take out the imbalance data problem, because each class, no matter how many samples are there in the class, they contribute equally in your final metric. So for example, if you have a class with only 10 samples and the other class with 1,000 samples, and so each of those will contribute 0.5 in your final measurement. So if you have 10 for the 10 sample class, you only have 2 samples correctly predicted, then you have an IOU measure for that particular class at 0.2. And for that 1,000 sample class, if you predict all of the samples correctly and you have IOU measure of 1 for that particular class, then you average over, you only have 0.6. But if you're using the sample accuracy, you will have an accuracy close to 1, which is not a good estimate of the real performance of your model. So this is the first testing line, and here is another testing line. And again, this is a ground truth that from a manually picked from an interpreter's manual interpretation, and this is the predicted result. As you can see that those 2 images again matches pretty well, and the main thing to notice is, although the boundaries are not matching perfectly, but we have a very clean body within each of the fishes, which makes the subsequent steps, such as generating geobodies, much easier. And also for this particular case, for this predicted result, it matches the reflector matches the reflector pretty well. So I think we're happy with this this result, and we can visualize it in 3D. So here we have a inline and a cross line of seismic amplitude, and we can overlap our prediction on this on those 2 lines. Well, actually, we have a volumetric prediction everywhere. We just show 2 lines, and this display is very useful for interpreters, because it gives you all the highlights or all the regions of interest that the interpreter may be interested in. Although those reasons are not 100% accurate, but it's very easy to find your interest with this color-coded map, and instead of just scanning through line by line without any highlights. And again, we can visualize those features in 3D as some sort of geobody. And as you can see here, we have very nice, well-defined gas chimney and all the other fishes as well. And you can crop it to whatever display you would prefer. So the second application I want to discuss today is fault detection. And here is a data set that we want to test our fault detection. And again, this data set is from offshore New Zealand, but from a different basin. So here we're in Great South Basin. A typical workflow of fault detection will start with some sort of edge detection attributes, for example, coherence. So here we have a coherence co-blended with the seismic amplitude. And as you can see that the coherence does a pretty good job to highlighting those faults. But there's some problem with this coherence attributes, because the coherence being a edge detection algorithm, it detects all the discontinuities in this data set. For example, here we have a bunch of very high coherence anomalies, but in this particular example, it's very low in value coherence anomalies, and those are not faults. So people call those things center races, which means they are cracks formed in the shale formation when the formation lost water. And another problem I would say for this image is if we take a very close look on this coherence image, we see some stair-step artifacts, which means the coherence anomaly along the fault surface is not smooth. Instead, it's highly segmented, and it related to some algorithm limitations in this kind of algorithm because it uses a vertical window. And so to get a better fault detection result, or to get a better initial attribute that we can run our fault surface generation algorithms on, we did some studies using neural network. So this is the result from convolutional neural network fault detection. And as you can see that here we have very smooth fault and with almost no noise at all from other types of discontinuities. And let me flip back to this coherence, and let's go to our CNN. So you can see that we have very well-defined faults with almost no noise at all. So this is a very promising result. And so how to get this result? You may ask a question that, well, there are several ways that we can do fault detection using CNN, and there's some of those are very easy to implement, and some of those may require some well-designed algorithm. So let's start with something basic. The most basic way, or the most naive way to implement the CNN-based fault detection is to do something like that. We define this problem as a classification problem, and we pick some training data to represent faults, and another set of training data, or sorry, another class of training data to represent non-fault. So here, all those green lines are the training data, the training samples picked to represent faults, and all those green rectangles are the red triangles are what we picked to represent non-fault. And I picked those things on 5 lines. And here are the coherence image that just to show you how the fault look like on the seismic data. And being a naive implementation, the algorithm we use is something like that. So for every sample, and we extract a small 3D patch around the sample, and we classify this small 3D patch to be whether it's a fault or non-fault, and assign this value to the center point. And in this way, we can, after we train this model, we can classify all the samples in the seismic volume one by one by using a sliding window and the size of this 3D patch. So this is the result from this naive implementation. Well, I would say this result is kind of ugly because the faults are relatively thick and they're not that continuous, and we have a lot of noise here as well. So at that time, we were thinking to clean it up using some image processing techniques. So we took this result and went through a image processing workflow, and I called it regularization, which is nothing but sharpening the fault, smoothing the fault along the fault and sharpening across the fault. So after this regularization, we have a result like that. To compare against our raw CNN output, as you can see that we have much sharper fault images, and it cleaned up those noise quite well. But at this time, you may ask that who actually does the heavy lifting? Is that the CNN, or is actually this image processing regularization? To answer this question, we brought in our coherence image and went through exactly the same regularization or image processing workflow, and this is what we got. So to compare this one with the one we got from using the CNN fault detection as our route output, well, it's pretty clear that once we use the CNN as our initial fault detection attribute, we get rid of those bunch of those type of noise. And moreover, we have a more continuous fault as well, compared to using this coherence. And to do a further comparison, we also did a fault detection using a swarm intelligence workflow from a third-party vendor that cannot tell the name. So this is the result from a swarm intelligence fault detection. And as you can see that it brings out most of the faults pretty well, but the problem is it may be too sensitive to the discontinuities, and you have those responses almost everywhere in your data set. And you have maybe those things are actually acquisition footprints or maybe some sort of noise. So if we use this example, sorry, this result to do a fault surface generation, you may have a bunch of fault surfaces that are not real. And to then we zoom in this box region, and on the left you have CNN-based fault detection, and on the right is coherence-based fault detection. And it's pretty clear that we don't have that kind of noise on here, and also the faults are very, very continuous and clean. And then again, here is a swarm intelligence, and we have a bunch of noise here, which may not be the real fault. And then we can view it in a vertical slice. Here is a coherence-based, and here is a CNN-based. So coherence-based and CNN-based. And it's pretty clear that the coherence-based result, even though we went through this regularization step, the fault surfaces are not that continuous, and we have a bunch of other types of discontinuity response as well. But for the CNN, it get rid of most of those, and the faults are very continuous and sharp. But then you may identify a problem. So this result is not as good as the one I showed at the very beginning. So what's the problem? And there's a lot of faults are missing, and but in general, it's just not that good. So as I said, this is a very naive implementation. So at the time that we developed this, and without maybe we can use a similar approach as we did for the seismic facies classification, and use that types of CNN network, and this is what we got. So this result is the same as the one I showed at the very beginning. The only difference is here I used this image processing regularization to make those faults a little thinner. So again, we can use different types of neural network, and this is just one possible way to do it. And this is similar to the one we can use for seismic facies classification. And we take a whole seismic line if your data is relatively small, or we can take a very huge 2D patch of data, say maybe 200 samples by 200 samples in size, and feed it into the network, and we get a classification at every sample in this patch simultaneously. So once we moved to this kind of algorithm, we will have a much better defined fault image, and we can then to make the faults even thinner by using some morphological thinning, which is just skeletization to make everything like one sample thick on a particular line. And to look from a time slice, this is the naive implementation, which I called a 3D patch-based classification. And this is the segmentation. But here, this segmentation network only runs on 2D, which means it takes 2D image for training, and then you can run your prediction on both inline and crossline and sum it together. So it's a pseudo 3D, but actually it's a 2D. So but even it's in 2D, it still gives you a better result compared to the 3D patch-based method. As you can see that you have much more faults and more continuous faults. And after that, we thought, okay, this result is okay, but we're only using 2D information. We train it on 2D lines. So can we use a 3D information and train a 3D CNN neural network? Well, the answer is yes. So this is the result that we got from training a real 3D neural network on this same data set. And to compare this result with this line-based CNN, I would say that it gives about the same faults, but in general, the faults are cleaner and the faults are more continuous. But moreover, the biggest advantage of this 3D scene fault detection neural network is to train this network, I don't need to use any prior knowledge for this particular data set I want to predict. So this network is trained on the data that not seen on this data set. So in other words, this network is very general, so that we can apply this trained neural network to many seismic data sets, as long as those are the data quality are relatively the same, or it allows a certain variation in the data set, but if you have, let's say, if you have a marine data, you're trained on the marine data and predicted on the land data, probably it's not gonna work. So so it still have some limitations in data quality, but in general, it works very, very well. And if you take the training time away from the user, so when the user use this type of technique to predict a fault, it becomes very, very fast. For example, in this particular data set, this data set about 1 gig, maybe 900 megabyte or so, and it only takes about a minute or even less than a minute to run on a single GPU. And another thing that we tried is to run a fault detection using some input data other than seismic amplitude. And in this particular example, I tried to run a fault detection using the self-organizing map classification result. The reason behind it is because some attributes, for example, the phase attribute, instantaneous phase attribute, or some cosine of instantaneous phase, all those attributes are very, very good to make your reflector very continuous. And it's so continuous in a way that it highlights the discontinuity between your continuous reflectors. So if we use those type of attributes and run a sum and get a classification result on those type of attributes, for example, like that, then we have a pretty clear, well-defined faults as well. So I trained my neural network on this image and hoping to see that they can pick the faults as well as, as good as the trained on the seismic amplitude data, or maybe even better. So this is the result we get from training a fault detection neural network on the sum classification result. And as you can see that it picks out the faults really, really well. And we may have a little bit missing faults here, but in general, it gives you a very good result on the fault detection, even though we're not using the seismic amplitude data. So at the very beginning, I was hoping maybe this result won't be as good as using the seismic amplitude, because we're limiting the information that we provide to the neural network. But in fact, it just did a pretty well job. And maybe the reason behind it is we carefully chose the attribute that's very very good to highlight those faults. We're not actually highlighting the faults, but it's highlighting the continuous reflector, so that the faults stand out on those attributes. And again, we can show this display the same fault on the seismic amplitude, and this is how they look like on the seismic amplitude. And let me flip back to the sum and to the seismic amplitude. As you can see, those faults are very well defined. Okay, our last application is for channel extraction. Well, this channel extraction is actually similar to what we did for the seismic facies, but just in this case, we're interested in a particular feature. So this data set is from offshore New Zealand in Taranaki Basin, but it's a different survey compared to the very first one that I showed. So here in this survey, we have a lot of channels, and most of the channels in this part are relatively small scale. And here we have a very big channel in the shallower part. And in this particular example, I'm interested in extracting this big channel from this data set. And as you know, that extracting those smaller scale channels are actually easier than the big ones, because for smaller channels, you can just use the coherence response from the channel flanks or the channel edges, and maybe the curvature response from the bottom of the channel. And those responses kind of overlaps with where the channel are, and you can just extract the channel body using those attributes. And but the problem with the big channel is, for the big channel, those attributes are only sensitive to the edges of the channel or to the bottom of the channel, but so it's only sensitive to part of the channel, but not the whole channel. So that makes extracting the whole channel somewhat challenging. So in this example, I manually highlighted this channel on several lines of in the data, and then after training the network, I extract channel over the whole volume, and this is what I got. So this channel matches the boundary of the channel boundary on the seismic pretty well. Let me flip back. And well, we may have some disagreement in here, but in general, I think in terms of get a quick interpretation of this channel, I think the neural network does a pretty good job. And we can, of course, see it in a 3D. And here on the lower right corner, we have the channel displayed on each of the time level, and I will grow from the bottom to the top, as you can see it. So for on every time slice, the channel matches the boundary on the seismic data pretty well. Let me go back and go back up again. So then I looked into another channel in the deeper part of the same survey. So here we are about 2 seconds. The previous one about 0.7, I think. So here we have a more sinuous channel and in the deeper part of the survey. And again, I picked some of the appearance of the channel. And after training the network, and we were able to match the channel boundary pretty well using this CNN classification. And of course, we have some disagreement or some noise that leaked outside of the channel, but that's I'm not too worried about that, because this is the raw output from the neural network without any post editing. So again, we can visualize it in 3D, and so the channel develops from this side, and once we grow up, the channel we can see this sinuous channel start to show up in this side, and it matches the boundary pretty well. And of course, we have some noise, and those things can be cleaned up by some post editing techniques. So conclusions. I think after I showed those 3 applications, it's safe to say that deep learning methods represented by convolutional neural networks are powerful in quantifying complex seismic reflection patterns into uniform facies, whether we're interested in multiple facies at the same time, or we're interested in a particular feature of interest, such as faults or channels. And we demonstrated the application for those 3 problems with clear success. And finally, I think that with great flexibility in model architecture, or with different types of CNNs, and with all your clever genius researchers, we can develop something particular for a particular problem, so that we believe that CNNs are promising in other interpretation tasks as well. I would like to thank Geophysical Insights for the permission to show this work, and I also want to thank New Zealand Petroleum and Minerals for providing those beautiful data sets and used in the study to the general public.